Hello, welcome to this discussion of our chapter 2 of complex variables, form 1. Today we are going to look at representing complex number on a complex plane, or representing a complex number on a Argand diagram. So I also look at properties of complex number. So for any complex number z is equal to x plus iy, in this complex number we can form coordinate points out of the imaginary and the real part, so that when we plot these generated coordinates on xy plane, it is represented on a complex plane. So z is equal to x plus iy. We need to identify the imaginary coordinate and the real coordinate, whereby x will represent the real coordinate and y will represent the imaginary coordinate. So if we plot x on the x plane, which is the same as the real axis, and we also plot y on the imaginary axis, we shall have x on real axis and y on imaginary axis. So if these 2 points are plotted, are joined together, they form a complex plane, or this complex number will have been represented as a diagram, and this diagram is what we call the Argand diagram. And this line from the origin can be determined by squaring the components, that is x component and the y component, or the real part and the imaginary part of the complex number z is equal to x plus iy. And this angle theta is got by, we had earlier looked at how to get this theta. This theta is obtained by take the arctan of imaginary part divided by the real part. So if you take the arctan of imaginary part divided by the real part, you will get this angle theta. Let's look at some examples on how we can represent some complex numbers in a complex plane. Represent the following complex numbers on a Argand diagram. We have a, z is equal to 3 plus 2i, b, z is equal to 4 minus 5i, and c, z is equal to minus 2 minus i. So this can be put on the diagram, and that is Argand diagram, whereby we have the imaginary axis and the real axis. So our task is to identify the real axis, the real coordinate, and the imaginary coordinate. So we have 3 for part A. 3 is the coordinate on the real axis, and 2 the coordinate on the y axis or imaginary axis. So we shall plot 3 against 2, which will be at this point. So this point represents z is equal to 3 plus 2i. Then b, you have z is equal to 4 minus 5i. So this would be 4, then minus 5. So we have 4 at this point on the real axis, and then minus 5 on the imaginary axis, which would be at this point, and this point will represent z is equal to 4 minus 5i. Then lastly, z is equal to minus 2 minus I. So we shall have minus 2 for real axis, and then minus 1 for imaginary axis. So this is minus 2 minus 1, which is at this point. So this point represents the complex diagram of z is equal to minus 2 minus I. So there are some numbers that you can try. So this is your exercise. Represent the following complex numbers on the Argand diagram. A, z is equal to 3 minus 6i. B, z is equal to 5 minus 5i. C, z is equal to minus I. D, z is equal to I plus 5. E, z is equal to 12. And F, z is equal to minus 6 minus 8i. Maybe to give a brief hint on how to plot 12, here this is a number which is purely real, meaning that the imaginary part is 0. So here we shall plot 12, then 0. Then for z is equal to minus I, this is purely imaginary, so we shall plot 0 minus 1. Then the next is properties of complex numbers, and they are mainly 3, that is commutative, associativity, and distributiveness. So let's begin with commutativity. Addition and multiplication of complex numbers are commutative. That is to say, for any two complex numbers, z1 and z2, z1 plus z2 is equal to z2 plus z1. So for the two complex number to be commutative, this equation must be true. And also for multiplication, z1 times z2 must be equal to z2 times z1. Then associativity as the second property. Addition and multiplication of complex numbers are associative. That is to say, for any complex number z1, z2, and z3, then we shall find that into z1 plus z2 plus z3 will be equal to z1 plus into z2 plus z3. And then for multiplication, z1, z2 times z3 is equal to z1 into z2, z3. The third property is distributiveness. Multiplication of complex number is distributive with respect to addition. That is to say, if you have complex number z1, z2, z3, then z1 into z2 plus z3 is equal to z1, z2 plus z1, z3. Let's look at some examples. Prove that the multiplication of complex numbers is commutative. So we have said that if you have two complex numbers, they can be commutative. So let's see how we can prove. If you let z1 is equal to x1 plus iy1, and z2 is equal to x2 plus iy2. Then we want to prove that z1 times z2 is equal to z2 times z1. So let's begin here. So here we shall have x1 plus iy1 times x2 plus iy2. If you open brackets here, we shall have x1 times x2, which will be x1 x2. Then the next will be x1 iy2, which will be ix1 y2. And then the next will be iy1 x2, which will be ix2 y1. Then the next will be iy1 times iy2, whereby I times I gives us I square y1 y2. So we shall find that we have x1 x2 plus ix2 y1 plus ix1 y2 plus I squared y1 y2. So we can pull out x2 in these two terms because it is common. So we shall have x2 into x1 plus iy1. Then these two terms, we have y2 being common, iy2 being common, we can pull it out. So we shall have iy2 into x1 plus iy1. So if in these two terms we have x1 plus iy1 being common, we can factor it out, and we shall remain with x2 plus iy2 into x1 plus iy1, whereby x2 plus iy2 is z2, x1 plus iy1 is z1. So this proves that if you have z1 times z2, it will give us z2 times z1. So this proves the commutative of complex number. Then example 2, prove that the multiplication of complex number is associative. So if we let z1 to be x1 plus iy1, z2 to be x2 plus iy2, and z3 to be x3 plus iy3, we shall find that these three complex numbers are associative. And this we can prove it by having z1, z2 times z3. So our task is to prove that z1, z2, z3 is equal to z1 into z2, z3. So let's begin. So here we shall have z1, which is x1 plus iy1, into z2, which is x2 plus iy2, then times z3, which is x3 plus iy3. So here we shall open brackets slowly. So we shall have x1 times x2, which is x1 x2, then x1 times iy2, which will be ix1 y2. Then you go to the next term, iy1 times x2, which will be ix2 y1. Then the next will be iy1 times iy2. So we shall have I squared y1 y2 times the z3, which is x3 plus iy3. So we still go ahead and open the brackets. We shall have x1 x2 multiplied with x3. We shall have x1 x2 x3. In the next we shall have x1 x2 times I y3, which will be I x1 x2 y3. Then we got the next term ix1 y2 times x3, which will give us ix1 x3 y2. Then we got the next ix1 y2 times y3, which will give us I squared x1 y2 y3. Then we go to the next term, which is ix2 y1 times x3, which will be ix2 x3 y1, then ix2 y1 times y3, which will give us I squared x2 y1 y3. Then lastly, we got I squared y1 y2 times x3. This gives us I squared x3 y1 y2 and I squared y1 y2 times I y3 gives us I power 3 y1 y2 y3. So from here we can simplify it by having x1 x2 x3 ix1 x2 y3 plus ix1 x3 y2 minus, since I squared is a minus, x1 y2 y3 plus ix2 x3 y1 minus x2 y1 y3 minus x3 y1 y2 minus y1 y2 y3, since I power 3 is a negative I. So from here we can simplify it, and here we're going to simplify it by pulling out x1, then also pulling out y1. So we shall have, since we need the first in our proof is to be z1, so let's pull out x1. So x1 here, if you pull it out, we shall remain with x2 x3 plus ix2 y3, then plus ix3 y2, then the last term will be y2 y3. You close the bracket, then plus. So here we can pull out iy1 since it is common. So we shall have iy1 into x2 x3 plus we have pulled out I, so to create a negative here we shall introduce I x2 y3. So we shall, the next will be I x3 y2, then the last one will be minus y2 y3. So since this term, the whole of this term is the same as this term, so what we do, we still factor it out. So we shall have x1 into iy1 into x2 x3 plus ix2 y3 plus ix3 y2 minus y2 y3. So we can go ahead and factorize x3 plus x2 x3 plus ix2 y3 plus ix3 y2 minus y2 y3, and this can be done. If we pull out x2, we shall have x3 plus iy3. Then here, if we pull out iy2, we shall have x3 plus iy2. So we shall have this term being equal to this term. Since they are the same, we can factor them out. So we shall finally have x1 plus iy1 into x2 plus iy2 times x3 plus iy3, and x1 plus iy1 represents z1, so we shall substitute there z1. x2 plus iy2 represents z2, so we shall substitute there z2. Then finally x3 plus iy3 represents z3, so we shall substitute z3. So we shall finally have z1 into z2 z3, and this proof is a proof that the complex numbers are associative. Then example 3, prove that the multiplication and addition of complex numbers are distributive. So this can be done by, if we let z1 is equal to x1 plus iy1, z2 is equal to x2 plus iy2, and z3 is equal to x3 plus iy3. This will be written as z1 into z2 plus z3 is equal to z1 z2 plus z1 z3. So we are required to show that if you have three complex numbers, then this equation is true. So we can begin from the left hand side by saying that z1 into z2 plus z3 is equal to, we substitute z1 which is x1 plus iy1 into z2 plus z3, which would be x2 plus iy2, then plus into x3 plus iy3. So here we shall open the brackets, so we can first begin with the whole of this term multiplied in this, then we also do the same multiplied in the next term. So we shall have, or we can have x1 multiplied in the whole of this term, and in the, then x1 multiplied in the second term. Also we do for iy1 for both the two terms. Now, so from here we shall have x1 into x2 plus iy2 and plus x1 into x3 plus iy3. Then we go to iy, so we shall have iy1 into x2 plus iy2, then plus iy1 into x3 plus iy3. So we shall have this expression. You can still go ahead and simplify it by opening the brackets. We shall have x1 x2, then plus I x1 y2, then the next will be x1 x3 times plus I x1 y3, then the next will be iy1 x2 I x2 y1, and next iy1 times iy2, which is I squared y1 y2. Then we shall have iy1 x3 plus iy1 times iy3, which gives us I squared y1 y3. So now we can factor out the x1 from this. So we shall have x1 into x2 plus iy2, which is here. Then the next term we can factor out iy1, so we shall have iy1 into x2 plus iy2, which will remain here. Then we can also pull out x1, so we shall have x1 into x3 plus iy3. Then we pull out iy1, so we shall have iy1 into x3 plus iy3. Then since this term is the same as this, so we shall factor it out, and we shall remain with x1 plus iy1 into x2 plus iy2. Then since this term also is equal to this, they are the same, so let's pull it out. So we shall have x1 plus iy1 into x3 plus iy3. So this one automatically is equivalent to z1, and this second term is equivalent to z2. Then this term here, after adding the first term, it is equivalent to z1, and then this second term here is equivalent to z3. So we shall substitute this one z1, z2, then plus z1, z3. So we can clearly see that this is equal to this expression. So from this we shall have proved that the complex numbers are distributive. Thanks for watching this video, and our next discussion will be on absolute or modulus or norm or magnitude of a complex number.